Hello, welcome back to EEE101. Today we will talk about source-free RC circuits. Source-free means that the circuit that we will analyze does not contain any independent sources. And RC means that circuit will contain resistance and capacitance. Before we discuss RC circuit, let us first talk about switches. A switch is a equipment which has two states, either an open state or a short circuit state. The way this switch is shown between node A and B, this is open circuit or the switch is open. We can operate the switch and close it at t equal to 0. So if we look at the switch, before the switching operation, the switch is open circuit, and after the switching operation at t equal to 0, the switch is short circuit. So we can describe the operation of the switch by these two statements. Switch is open for t less than 0, the switch is closed for t greater than 0. Now we look at the another configuration of the switch. Here the switch is closed. At t equal to 0, we operate the switch and the switch becomes open. So the two states of the switches are now different. Before the switching or for t less than 0, the switch is closed or AB is short circuit. After the switching or for t greater than 0, the switch is open or AB is open circuit. Switches are usually not shown in electrical circuit with such details. The circuit symbol for each configuration of the switch that we will use are like this. First, the switch is always shown as an open circuit. The time of the switching action is written near the switch and the arrow indicates the direction of the switching operation. So here the switch is pushed, the switch lever is pushed downward. This corresponds to this switching action. So this circuit symbol will represent a switch with these properties. On the other hand, if I want to represent the right switch with a circuit symbol, everything else will be the same, but the direction of the arrow will be opposite. In this switch, the lever is moving such that it is opened from closed condition. So this is the circuit symbol of the switch described by these two conditions. Now that we understand how to represent these switches, remember that these switches are called single pole single throw switch. There is one pole and the switch can be thrown in only one way between two nodes. There is another type of switch which involves three nodes. This is that switch. As shown, the switch is connecting node A and node B. The switch is always connected to node A. This is the pivot and the lever goes either to node B or to node C. In this condition, A and B are closed or short circuit. A and C are open or open circuit. At t equal to 0, we throw the switch. So after the switching now, A and B becomes open circuit and A and C becomes short circuit. So this switch can be described by these properties. For t less than 0, AB is short circuit, AC is open circuit. The situation reverses after the switching, that is for t greater than 0. And BC is always open circuit. This type of switch is represented in electrical circuit by this symbol. Here again the direction of the arrow indicates how the lever is thrown at t equal to 0. Here again we have a single pole, but there are two possible ways for throwing the switch. So this type of switch is called single pole double throw or SPDT switch. Okay, we have understood basic type of switches. Now we can discuss discuss source-free RC circuits. Let's look at this circuit. Here we have a capacitor C, a resistance R, and a voltage source V0 in series with a resistance R0. There is a two-way switch or SPDT switch. For t less than 0, the switch is at node B. For t greater than 0, the switch is at node C. Our objective is to find the capacitor voltage after the switching or for t greater than 0. So we draw the two circuits separately for t less than 0 and for t greater than 0. This is the circuit for t less than 0. We always look at that part of the circuit which contains the capacitor. And for t greater than 0, this is the circuit. You can see that for t less than 0, there is an independent source in the circuit, but there is no independent source in the circuit for t greater than 0. That's why this is called source-free RC circuit. Normally in a resistive circuit, if there is no independent source, there will be no voltage, no current. But the situation is different in RC circuits if there is a capacitor, because the capacitor can store energy and supply the energy to the resistance, producing current and voltage. Okay, we will now analyze each of these two circuits separately. First, we look at the circuit for t less than 0. Here, the voltage source V0 will be charging the capacitor. Once the capacitor is fully charged, all the voltages in the circuit will become constant. The current will also not change with time, and the DC condition will be realized. Remember, DC condition means the voltage and current in the circuit are not changing with time. And from the property of the capacitor, we know that at DC, C behaves as an open circuit. So we can replace this capacitor as an open circuit this way. And in this open circuit, there is no current. So R0 is ineffective and VC is equal to V0. And this condition is valid for t less than 0. Remember that 0 minus, which we discussed earlier, is less than 0. So this condition also holds for 0 minus. So we can say Vc0 minus is equal to V0. We also know from the property of the capacitor that capacitance voltage is a continuous function of time. In other words, the value of the capacitance voltage at 0 minus must be equal to the capacitor voltage at 0 plus. So using the continuity condition, we can complete this expression in this way. Here 0 minus is the time just before the switching and 0 plus is the time just after the switching. And we have obtained the relationship from the circuit for t less than 0, but from this circuit we have obtained the value of the capacitant voltage at 0 plus, which is t greater than 0. That means this circuit has provided us the initial value of the capacitor voltage for t greater than 0 circuit. For this reason, this expression is known as the initial condition, and this V0, which is equal to Vc0 plus, is known as the initial value. We now analyze the circuit for t greater than 0. This was the circuit. We assign a current through the capacitor IC and another current through the resistor IR. Writing KCL at the plus node, this is what we get. Vc is the voltage across the capacitor as well as across the resistor. So the currents can be expressed in this way. This is from the IV relationship of the capacitor, and the second term comes from Ohm's law. This term can be rearranged in this manner. And if we integrate this equation, we find this equation. Here, ln of A is a constant of integration. A is not known. Okay, if we shift ln A to the left side, and remembering that ln of x minus ln of y is ln of x over y, we can write the equation in this way. We need to find the constant of integration A. To do that, we look at the capacitor voltage at t equal to 0 plus. At t equal to 0 plus, if we put t equal to 0 here, the exponential becomes 1, and we can say Vc0 plus is equal to A, which we identified from the circuit for t less than 0, that Vc0 plus is V naught. So A is equal to the initial value of the capacitor voltage. In this circuit, C and R are constants. So the product RC is also a constant. It can be shown that the unit of R and C product is seconds in SI system. So this is the time. RC is known as the time constant, and it is represented by the Greek symbol tau. So considering these two, we can write that the capacitor voltage is V naught e to the power minus t by tau for t greater than 0. This is our desired result. We now want to see how this capacitor voltage varies with time. We want to look at that graphically. At t equal to 0, the exponential term is 1, so the capacitor voltage is equal to V naught, which is the initial value. At t equal to infinity, e to the power infinity is 0. So the capacitor voltage is 0. In other words, between t equal to 0 and t equal to infinity, the capacitor voltage decreases from V0 to 0. How is the variation? That variation is shown in this graph. It decreases like this, and this is a very well-known curve which is known as the exponentially decaying function. This function has many uh, practical applications in mathematics and in electrical engineering. Now, what is the significance of tau? If I put t equal to tau here, then the capacitance voltage is V naught e to the power minus 1, which is equal to 0.368 V naught. So it can be argued that the time constant tau is the time when the capacitor voltage is 36.8% of the initial value. Okay. Now mathematically, an exponentially decreasing function becomes 0 only at t equal to 0. But this is not a practical engineering condition in real application. We want to adopt a more realistic condition when we can call the capacitor voltage 0. The commonly used definition says that the capacitor voltage may be treated as 0 when its value is less than 1% of its initial value. In other words, if V0 is equal to 100 volts, and when the capacitor voltage goes below 1 volt, we will, for most practical purpose, say that the capacitor voltage has become 0, or the capacitor has completely discharged. Now the question is, how much time will it take for the capacitor voltage to become less than 1% of its initial value? To find the time, we look at this chart. At t equal to tau, this is 36.7%. T equal to 2 tau, this is 13.5%. T equal to 3 tau, this is 4.9%. All these values are greater than 1%. But at t equal to 5 tau, this is 0.6%. So we can say that the capacitor voltage becomes less than 1% of its initial value after 5 tau time. So how much time does it take for the capacitor voltage to become 0 from practical consideration? The answer is 5 tau. For practical purpose, the capacitor voltage becomes 0 after 5 tau. So this is the condition that we will use in our electrical engineering applications. Okay, now we want to see how the function changes when the value of tau is changed. We can change the value of tau. We can change the value of tau by changing the value of r if c remains constant. Here we show three graphs. The green graph is for tau equal to 0.5 second. The blue graph is for tau equal to 1 second. And the red graph is for tau equal to 2 seconds. We can see that the graph for tau equal to 0.5 seconds decays most quickly, and the graph for tau equal to 2 seconds decays most slowly. So the general observation that we can make is that the smaller the value of tau, the quicker the capacitor voltage decays, or the larger the value of tau, the slower the capacitor voltage decays. This concept is very important in many practical electrical engineering applications. Okay, to determine VC in a circuit, in a source-free RC circuit after the switching, we need to know V0 and tau. The analysis circuit that we have considered contained only one resistance R, but often circuits will be more complicated than having a single resistance. They may contain a network of resistances, they may even contain dependent sources. The question is how to find V0 and tau in those circuits. To find V0, we look at the circuit at t less than 0. And in this circuit, we consider DC. That means the capacitor is treated as an open circuit. So we make an open circuit between the two nodes where the capacitor was, and the voltage across the open circuit is our V0. So this is the way to determine V0. To find R, we considered the circuit for t greater than 0, and R is Thevenin's equivalent resistance between the two nodes where the capacitor is connected. In the language of electrical circuits, we say that R is equal to Thevenin's equivalent resistance seen by the capacitor. So these are the two conditions which allow us to find V0 and R in a source-free RC circuit. And once we know R, tau is simply equal to the RC product. And once we know V0 and tau, we can write the expression for the capacitor voltage. Now let us look at a problem. In this circuit, the switch was initially closed. At t equal to 0, the switch has been opened. We want to find the capacitor voltage for t greater than 0, and we want to sketch the voltage. Okay, remember, first we considered the circuit for t less than 0 and consider the capacitance as open circuit. So this is the circuit that we get. For t less than 0, the switch is closed and the capacitor is replaced by an open circuit. We need to find V0. The 50 ohms resistance is in series with an open circuit, so this is ineffective. The two 200 ohms resistances are in parallel, so their equivalent is 100 ohms. So now we have a very simple circuit, a 100 ohms resistance connected to a 0.1 ampere current source, and the voltage V0 is across the 100 ohms resistance. So using Ohm's law, we can say V0 is equal to 10 volts. To find R, we have to look at the circuit for t greater than 0. For t greater than 0, the right part of the circuit has been disconnected. The capacitor was here, so R is equal to the RTh seen by the capacitor. This is straightforward, case 1 for finding RTh. The two resistances are in series, so R is equal to 250 ohms. Tau is RC. If we do the calculation, tau is equal to 5 times 10 to the power minus 3 seconds or 5 milliseconds. We know V0, we know tau. So Vc is given by this expression 10 e to the power minus 200 t volts for t greater than 0. This 200 is equal to 1 over tau. Okay, so we have obtained the capacitor voltage. Now we want to represent this voltage graphically. We know that the capacitance voltage for t greater than 0 decays exponentially. So for t greater than 0, the capacitance voltage looks like this blue line. For t less than 0, the voltage is constant at V0, which is 10 volts. We have to show t equal to tau in this graph to indicate the nature of the decay. At t equal to tau, which is 5 milliseconds, the capacitor voltage is 36.8% of the initial value. 36.8% of the 10 volts initial value is 3.68 volts. So this expression and this graph are our desired results from the solution of this problem. That is all for this lecture. Thank you.